All right, in this question, we're going to define the volt. So always sort of think about whether it's a quantity or a unit. Volt is a unit, right? It's a unit that measures voltage. And we talked about how there's different ways to sort of think about voltage. So let's say the SI unit of voltage, which is EMF and PD. But I would also try to sort of think of an equation like 1 volt equals 1 joule per 1 coulomb. So if you remember, sort of voltage is energy divided by charge. That's key to sort of defining the quantity voltage. So the unit volt is measured in what? Joules per coulomb. That's sort of, and again, these are not base units, but that's okay. So the SI unit of voltage, 1 volt equals 1 joule per coulomb, right? So getting this idea of what is a volt, it's a joule per coulomb. Okay, you don't have to go to the base units, but you should sort of express it that way. We've got a network of 3 resistors. The combined resistance of the 2 resistors connected in parallel. So that's our first job. Calculate the combined resistance of these 2 guys here. So this is a parallel branch, and so we'd solve it like 1 over the parallel resistance equals 1 over 100 plus 1 over 300, 1 over 100 plus 1 over 300. Let's see, that's 3 over 300, right? That's the same as 1 over 100. 3 over 300 plus 1 over 300 is 1 over the parallel resistors. So that's 1 over parallel resistors equal to 4 over 300. So that's 300 over 4. $75. Note that you're always going to get a parallel equivalent resistance that's less than any of the resistors connected in parallel. So 75 is less than 100 and less than 300 because that's the way that we add them, right? We're always adding reciprocals, so we're always going to get a lower number. The total resistance between the terminals X and Y. Well, they sort of set us up for success here, right? Because we've already done the hard part. We've calculated the combined resistance of the parallel part. We know it's 75, and now we can just sort of say, okay, we've collapsed this branch of the circuit down into 1 resistor equal to 75. It is in turn in series with this 55. So when we're thinking about calculating the total resistance between X and Y, it's simply the combined resistance of these, 75 plus 55, right? Because those 2 are in series, and so we get our sort of both of our resistor equations. So those 2 answers for this one to begin. Moving right along, it says the network in D is connected to a power supply so that there's a potential difference between X and Y. The power dissipated in the resistor of resistance 55 is 0.2 watts. Calculate the current in the resistor of resistance 55 and in the 300 ohm resistor. We want the currents in those given that information. So now they tell us what? We hook up a power supply, and all we know is the power dissipated in this one is 0.2 watts. That's all they tell us. They say, okay, hook up some source of EMF. And we're going to send some electrons, push some electrons through this. Some are going to go through here. We need to figure out how many are going through this one. Some are going through here. They all meet back up, right? Kirchhoff's first law, they're going to sort of combine right here and go through this 55 ohm resistor where we know a power is dissipated of 0.2 watts, okay? So from that information and sort of what we already are given here, we should be able to deduce the current, so through here and through here. Power equals I squared R. Power also equals V squared over R. Power also equals IV. So you might think, well, we could just calculate it simply. P equals IV. We know P, but we don't know V. we could perhaps deduce what V is using this equation, but then it would just be sort of using this equation to figure out V. So we could in turn, so it's like, well, if we're going to use sort of any equation possible, we might as well just use the one that includes the thing that we're solving for right away. So 0.2 watts equals I squared, that's the unknown, and R is the resistance there, 55. So we should be able to solve for I like this. 0.2 equals I squared, and then R is 55. So if we divide each side by 55, 0.2 over 55 gives us a small number. 3.6, 3 repeating, times 10 to the negative 3. And then we know that that's equal to I squared. So then we need to do what? Take the square root of that. So I get for I, and remember we've already solved these ones here. I get I equals 0.06 amps. Well, it's a low amount of power. Okay, so maybe there's not that many amps in it, right? So 0.06 squared times 55 is 0.2. So if you plug that back in, here, I squared times this R, that's the power dissipated. So it seems like there is 0.06 amps right here. And then we can think about this part of the circuit. We'd say, okay, we know that there was 0.06 amps that went into this. This is the path of more resistance. This is the path of less resistance. And so more electrons would go this way. How many more? Well, 3 times as many, right? Because this has 3 times the resistance of this. So you're sort of saying, what charge I plus, or what current I through here, let's say, plus what other current that's 3 times as much, right? Or rather, the 3 times as much would go this way. So what current I through here times 3 times as much current that would go through here again, because it's less resisting to the flow of charge. So 3 times the charges will go through this one. So you have I, the current through here, plus 3I, the current through here, will equal all of the I's, the 0.06 amps that we've already calculated. Or you could think about it like this, like the 0.06 comes in and splits up into these. So we've got 4I equal to 0.06. So I must be 0.015 amps. So if there's that many amps going through this way, multiply it by 3, there's 0.045 amps. They don't ask us about that, but that's how many are going through there. And if you add that to the 0.015, there's our 0.06. So Kirchhoff's first law helps us deduce that. And again, the ratio of the resistances tells you how much charge is going to go through. What is it resisting? It's resisting flow of charge. More charges want to go through the path of resistance. So we said that the current through the 55 ohm resistor was 0.06, which means the current through the 300 ohm resistor was 0.015. Calculate the potential difference between X and Y. So that's the total voltage drop sort of across all of this. Voltage drop between X and Y. So we know enough about this circuit now, we should be able to sort of calculate it all. The voltage across this is the same. Okay, so remember the voltage across parallel branches is the same. So we could think about it as V equals IR, and we could either use the 0.015 amps times this R, or the 0.045 amps times this R. And again, you'll see that, oh yeah, because this one was 3 times as much, there was a third the amount of charge. Because this one had a third the amount of resistance, there was 3 times as much charge. So it doesn't matter which V equals IR you apply, you'll get the same voltage across this. So I have my 300 ohms times my 0.015 amps. That's R, that's I, V is their product. And so there's 4.5 volts dropping across these nodes here. 4.5 volts available to both of these resistors, right? So then there's going to be a voltage drop, V equals IR across this. And again, we know that the I here is different. It's not the 0.015 or the 0.045, it's the 0.06 amps times 55. And so 55 ohms times 0.06 amps means that there's going to be 3.3 volts dropping across this. the total voltage drops are equal to the EMF, right? And so the terminal PD is sort of the potential difference between all of this. 3.3 plus 4.5 gives 7.8 volts. And so I think that's the last one on this question. The difference of 7.8 volts. Let's check the old one. So this was question number 5 from this paper. Start defining the volt. Question number 5. See how they have that joule per coulomb? 75 ohms, 130, 0.06, 0.015, 7.8. It looks like they have another path to the solution there. I think this is the way that we did it. Other valid methods are also possible. It says many paths to the same correct solution. What do they do up here? They got 130 times 0.06. And so where did that 130 come from? I guess that was, oh yeah, we already knew the total resistance. And so I times R, that's the total current times the total resistance equals IR. We just solve it that way. We did the drops across each one. So they both work.